Hello everyone. In this lesson, we will discuss the simulation of atmospheric and vacuum distillation. This unit is a petroleum atmospheric and vacuum distillation unit. The process flow includes a flash tower, atmospheric tower, and vacuum tower, along with an atmospheric furnace and vacuum furnace, totaling 2 furnaces and 3 towers. My presentation will cover 4 aspects. First, the process flow of crude oil atmospheric and vacuum distillation. Second, the conditions required for starting up atmospheric and vacuum distillation. Third, the startup procedure for the crude oil atmospheric and vacuum distillation unit. Fourth, oil charging and cold circulation. First, let's study the atmospheric and vacuum distillation process flow for crude oil. Crude oil is pumped by the crude oil pump to heat exchangers, where it is heated to 131 degrees Celsius. A certain amount of demulsifier and wash water are added, and after thorough mixing, it enters the first stage electric desalting vessel. Simultaneously, under the action of a high-voltage electric field, oil and water are separated. The dehydrated crude oil flows out from the header at the top of first stage desalting vessel. More demulsifier and wash water are injected, and after thorough mixing, it enters the second stage electric desalting vessel. Again, under the action of a high-voltage electric field, further oil-water separation occurs. The dehydrated crude oil flows out from the header at the top of the second stage desalting vessel. More demulsifier and wash water are injected, and after thorough mixing, it enters the third stage electric desalting vessel. Again, under the action of a high-voltage electric field, further oil-water separation occurs, achieving the purpose of crude oil electric desalting. Then, it is heated to about 200 degrees Celsius via heat exchangers, and enters the flash tower. In the flash tower, a portion of the light components is removed. The topped crude is then pumped to heat exchangers, where it is further heated to above 290 degrees Celsius, then goes to the atmospheric furnace, heated to 396 degrees Celsius, and enters the atmospheric tower. In the atmospheric tower, components up to heavy diesel are removed. The high boiling point heavy components are then pumped to the vacuum furnace, heated to 430 degrees Celsius, and enter the vacuum tower. In the vacuum tower, lubricating oil fractions are removed. The bottom residue is pumped to heat exchangers for cooling and then leaves the unit. The startup of atmospheric and vacuum distillation should meet the following conditions. First, pre-startup preparations. Second, inspection of equipment and production process. Third, steam purging. Fourth, pressure testing of equipment and pipelines. Fifth, diesel flushing and circulation. After the preparations are completed, the startup procedure is as follows: oil charging, cold circulation, thermal circulation, atmospheric system put into normal operation, vacuum system put into normal operation, and finally, putting the 1 desalting, 3 injections into use. Next, let's study the main process flow together. The crude oil is divided into 2 streams. One stream exchanges heat with atmospheric side streams. The other stream exchanges heat with vacuum side streams. The specific flow is as follows. Crude oil at 40 degrees Celsius is pumped from the tank farm into the unit and divided into 2 streams. The atmospheric stream exchanges heat successively with the crude oil ATM first side stream exchanger, crude oil ATM third side stream exchanger, crude oil ATM first intermediate reflux exchanger, and crude oil ATM second side stream exchanger, heating to 136 degrees Celsius. It mixes with the crude oil from the vacuum stream after heat exchange and goes to the electric desalting section. The vacuum stream exchanges heat successively with the crude oil VAC first side stream and overhead reflux exchanger, crude oil VAC second side stream exchanger, and crude oil VAC residue exchanger, heating to 134 degrees Celsius. It mixes with the crude oil from the atmospheric stream after heat exchange and goes to the electric desalting section. After desalting, the crude oil is again divided into 2 streams. One stream exchanges heat with atmospheric side streams, passing successively through the desalted crude oil ATM heavy diesel exchanger. Desalted crude oil ATM third side stream exchanger. Desalted crude oil ATM second intermediate reflux exchanger. Desalted crude oil ATM third side stream exchanger. And desalted crude oil ATM heavy diesel exchanger for heat exchange. After the temperature rises to 222 degrees Celsius, it mixes with the heat-exchanged crude oil from the vacuum stream and enters the flash tower T101. The other stream exchanges heat with vacuum side streams, passing successively through the desalted crude oil VAC third side stream exchanger, desalted crude oil VAC first intermediate reflux exchanger, desalted crude oil VAC residue exchanger, desalted crude oil VAC second side stream exchanger, desalted crude oil VAC third side stream exchanger, and desalted crude oil VAC first intermediate reflux exchanger for heat exchange. After the temperature rises to 208 degrees Celsius, it mixes with the heat-exchanged crude oil from the atmospheric stream and enters the flash tower T101. The overhead oil gas from the flash tower enters the 28th tray of the atmospheric tower T102. The flash bottom oil is pressurized by the flash bottom pump P102 and is again divided into two streams for heat exchange. One stream is heated to 321 degrees Celsius via the flash bottom oil VAC second side stream exchanger, flash bottom oil VAC second intermediate reflux exchanger, and flash bottom oil VAC residue exchanger. The other stream is heated to 295 degrees Celsius via the flash bottom oil VAC residue exchanger, flash bottom oil VAC third side stream exchanger, and flash bottom oil VAC second intermediate reflux exchanger. The two streams mix and then enter the atmospheric furnace F101. Below is the atmospheric tower section. The atmospheric overhead oil gas is exchanged in the overhead oil gas hot water exchanger, then air-cooled to 40 degrees Celsius by the overhead air cooler, and enters the overhead reflux and product drum for gas-liquid separation. The oil phase is pressurized by the overhead reflux and product pump P103 and divided into two streams. One stream returns to the top of the atmospheric tower as top cold reflux. The other is sent out of the unit as naphtha product. The water phase is pressurized by the overhead water pump and sent to the sour water stripper. The atmospheric first side stream oil flows from the 30th tray of T102 into the upper section of the first side stream stripper T103, where it is stripped with superheated steam. The vapor phase after stripping returns to the 34th tray of T102. The liquid phase is pumped out by the first side stream pump P106, cooled to 93 degrees Celsius via the crude oil/ATM first side stream exchanger and water cooler, then sent to the caustic wash unit. The atmospheric second side stream oil flows from the 20th tray of T102 into the middle section of the second side stream stripper T103, where it is stripped with superheated steam. The vapor phase after stripping returns to the 24th tray of T102. The liquid phase is pumped out by the second side stream pump, exchanged, then cooled to 135 degrees Celsius by the second side stream air cooler, and sent to the caustic wash unit. The atmospheric third side stream oil flows from the 9th tray of T102 into the lower section of the third side stream stripper T103, where it is stripped with superheated steam. The vapor phase after stripping returns to the 14th tray of T102. The liquid phase is pumped out by the third side stream pump, heated to 218 degrees Celsius by an exchanger, then cooled to 102 degrees Celsius by the third side stream air cooler, and sent to the caustic wash unit. The atmospheric first intermediate reflux oil is drawn from the 25th tray of T102 by the first intermediate reflux pump, exchanged to 200 degrees Celsius, and returned to the 29th tray of the atmospheric tower. The atmospheric second intermediate reflux oil is drawn from the 15th tray of T102 by the second intermediate reflux pump, exchanged to 275 degrees Celsius, and returned to the 19th tray of the atmospheric tower. The atmospheric residue is pumped out by the atmospheric bottom pump and divided into two streams. One stream is sent directly to the vacuum furnace F102, heated, and then goes to the vacuum tower for separation. The other stream is exchanged and then sent to the catalytic cracking unit. Below is the vacuum tower section. The atmospheric residue is heated to 430 degrees Celsius in the vacuum furnace F102 and enters the vacuum tower T104 for vacuum distillation. The vacuum overhead oil gas is extracted by the first stage vacuum ejector to the first stage overhead air cooler and cooled to 40 degrees Celsius. The liquid phase flows into the overhead decanter drum. The vacuum first side stream draw oil is drawn from the reservoir below the first packing section of T104 by the first side stream and overhead circulation pump, pressurized, exchanged, then cooled to 55 degrees Celsius by an air cooler, enters the stripper for stripping, and leaves the unit as a diesel blending component or catalytic cracking feedstock. The vacuum second side stream oil is drawn from the reservoir below the third packing section of T104 by the second side stream pump, pressurized, exchanged to 229 degrees Celsius, then cooled to 141 degrees Celsius by a water cooler, and leaves the unit as hydrocracking feedstock. The vacuum third side stream oil is drawn from the reservoir below the fourth packing section of T104 by the third side stream pump, exchanged to 220 degrees Celsius, then cooled to 155 degrees Celsius by a water cooler, and leaves the unit as catalytic feedstock. The vacuum first intermediate reflux oil is drawn from the reservoir below the second packing section of T104 by the first intermediate reflux pump, pressurized, exchanged to 172 degrees Celsius, and returned to T104. The vacuum second intermediate reflux oil is drawn from the reservoir below the third packing section of T104 by the second intermediate reflux pump, exchanged to 242 degrees Celsius, and returned as reflux to T104. The overflash oil is drawn from the reservoir below the fourth packing section of T104 by the overflash pump, pressurized, and returned to the bottom of the vacuum tower. The vacuum tower bottom residue at 390 degrees Celsius is pumped out by the vacuum residue pump, exchanged to 131 degrees Celsius, and leaves the unit. This is a schematic diagram of the cold circulation flow. No load is applied during the cold circulation stage. Here, the necessary conditions for distillation are pointed out. First, there must be a difference in volatility between the components in the mixture. Second, there must be temperature and concentration differences when the gas and liquid phases contact. Third, a place must be provided for intimate contact between the two phases, i.e., trays. Fourth, there must be liquid reflux at the top and vapor boil-up at the bottom. Crude oil fractionation towers share the same principles as general distillation but also have differences. For example, the atmospheric tower is a complex tower. The feed and products of the atmospheric tower are both complex mixtures. The atmospheric tower has a stripping section and strippers. The atmospheric tower often has intermediate circulating refluxes, and it has a certain amount of overflash. Crude oil dehydration and desalting are very necessary to avoid unstable operation of the distillation tower and salt deposition on pipe walls. The primary distillation tower can increase unit throughput and stabilize atmospheric tower operation. The heat for the atmospheric tower basically relies entirely on the feed. The reflux ratio is determined by the overall heat balance of the tower, leaving little room for adjustment. The vacuum tower has coarser requirements for fractionation precision compared to the atmospheric tower. Its role is to maximize yield while avoiding cracking reactions. Alright classmates, that concludes the DCS simulation for atmospheric and vacuum distillation. See you in the next class.